Hi, my name is Thomas Kramer. I'm the Chief Financial Officer at IonQ. I've worked most of my adult life in technology, and the other part of my adult life I've spent in universities, and I'm very happy to welcome you here.
Hello, I'm Dean Kastman. I run all of our engineering and technology here at IonQ, and so I'm responsible for all of the hardware and software development across our systems, so it's kind of our full stack software from cloud all the way down to our firmware. And on the hardware side, it's kind of like our ions all the way out to our enclosures. And so before IonQ, I worked at Blue Origin where I ran all research and development. And so I'm very happy to welcome you all here today.
Good morning. My name is Margaret Arakawa. I'm the Chief Marketing Officer for IonQ. I obviously work on Quantum Korea and meeting a lot of you in Korea, as well as customer engagement. Prior to IonQ, I worked at several startups. I've been in technology for 30 years, and I spent 20 years at Microsoft working on classical computing. So I'm super excited about quantum and welcoming you here.
Morning, everyone. My name is Jordan Shapiro. I'm the Vice President of Financial Planning and Analysis and Head of Investor Relations and Corporate Development here at IonQ. I've been at IonQ for about 4 years, and prior to joining IonQ, I was an investor in the company at a firm called NEA. Nice to meet you.
All right. Thank you for having us. I'll get right into the questions. The first one we have is, when do you expect IonQ systems to create real value that leads to significant revenue? And what kind of use cases do you foresee?
Great. So, well, I will start with, we are already generating significant revenue.
Right.
And I think what is amazing to me is I also started 4 years ago, and when I started, we had zero revenue, zero sales. And now our guidance for this year is 75 to 95 million, which means that we're close to 100 million in sales, which is reckoned to be a milestone for technology companies. And so from that perspective, we're doing really well. However, what we're also looking at, which I think you're looking at, is the market for quantum computing is reckoned to be so large that the 100 million is nothing. And that is actually the beauty of it. That's why we're here. And we see that we will continue to grow. We will give more guidance on next year's bookings and revenue come the Q4 call, which typically happens in February.
So what kind of use cases do you guys foresee?
So right now, we've been looking very aggressively at different use cases across the last 24 months. Right, trying to understand where we expect the hardware capability line to cross kind of the application line, right? And so in those, some of the top ones we've talked about before include kind of chemistry applications, right? Some of those are optimizations. And so optimization shows up in a tremendous amount of areas, whether it's logistics, whether it is even, job scheduling. We've had examples in the past with like Airbus and the DESI problems. Those are all examples of optimization problems. We've talked about kind of the kite algorithms and other kind of extensions to the classical kind of QAOA type of solution techniques. And so optimization is going to continue to be kind of a very rich type of opportunity. There's also some of the machine learning and object recognition, those kind of pieces, right? There's novel encoding techniques. So between the chemistry pieces, the optimization pieces, those are the big two. And then there's a whole number of additional smaller items.
I think there's 3 benefits from quantum that are massively different or significant enough that that's why people are investing in quantum. People want to be safe and secure. They want to be healthy, and they want to be efficient. Everything he said is about those things. We don't typically talk a lot about security, but as you know, there is a point in time when quantum might be able to break all of encryption. And for all of us who have bank accounts, we want our money to be safe, and we want personally to be safe. From a healthcare perspective, the reason why we invest is because drug discovery and curing cancer, those are on the docket for what quantum can do. So every individual wants to be healthy and live longer and efficient. Why do we optimize anything? Why do we have to optimize, flight gate assignments so that we're not running around airports and Airbus can save money and, sustain and not use as much fuel. So when you think about the vast benefits, are we going to be safer? Are we going to be healthier? Are we going to be more efficient? Those three things quantum can do at a massive scale that, classical has not been able to do yet.
And the next question, will the quantum applications be released very sporadically, or will there be clear growth in frequency with several apps per year after the first one is launched?
So we have spoken about the fact that on our upcoming earnings call, we'll share more about some of our plans for quantum applications. We haven't necessarily released a cadence of when those will come out, but we imagine as quantum compute enters the market more, yes, you'll see an increase of the number of applications. Those might come directly from IonQ, but they might also come from someone using us in the cloud or one of our customers. And so we expect, yes, the application space will grow, but we haven't produced any specific projections as to how quickly it will grow and when.
But at market maturity, just think about the App Store. A few years ago, we all actually never heard of an App Store.
Right.
And the first time it was introduced, it had some games and calculators and not much. And today, there is everything on the App Store, and there's always new ones coming in. That same thing will happen for quantum. We will not be directing the flow of applications in the mature state of this industry. We will all just benefit from it because everybody, all developers, or obviously not all, but there will be so many developers that if you try to control it, you can't, nor should you. It's that benefit we want.
And the next question is, what is IonQ's vision for its business models? I recall Peter mentioning that the Seattle facility will produce quantum computers in a Henry Ford style. Will selling quantum computers be the IonQ's primary business, or do you foresee other emerging revenue streams that could become significant?
Absolutely. And you can actually, you will see the floor later on, and you will appreciate what goes into creating a quantum computer. The main intention for us to build this facility was so that we could build replicable computers. So that they're not just so, like if you build your own car, only you can drive it. But if you buy one from a factory, you have a manual, every mechanic can fix it. And that was the main reason for us to have a completely separate facility, so that we would no longer be reliant on the people who develop the computers to also manufacture it, because you can't service things like that at scale. Because of the cost of quantum computers, of course that will be the main part of our revenue for some period of time. But if we look at how computing has worked, we should expect that at more mature levels of the industry, a lot of traffic will go through hyperscalers because everybody doesn't need a full quantum computer. And we should also expect that a lot of revenue comes from software, because when we think of computers and quantum computers to be great to hopefully one day contribute to curing cancer, it is not the machine that all of a sudden wakes up and blinky lights comes on and it creates chemical combinations. It is the application of the machine. That's all in software, and in soft software, people. And so we will have the ability to join this, and we are working on actually making applications. We expect that the software market for quantum will be larger than hardware at some point in time. And we hope to be part of that.
It is very analogous to the classical, right? There are hardware providers that still exist in the world that do classical.
Right.
There's software, like Microsoft level software, which is an OS, like what makes this computer work. But there's applications that sit on top of that. There's services that we sell. And the last announcement we had with Air Force Research Lab, that was about networking, right? It was about our expansion into another area where now these quantum computers have to be networked. They have to talk to the current computers that are out there. So those are all the businesses that we have recently, and all the way since when we first went public, talked about where our revenue streams would come from.
Talking of quantum networking, I have a question related to that. So IonQ has been securing quantum networking related contracts from AFRL and from ARLIS. Is the quantum networking business a new venture, and how large is this business expected to grow compared to IonQ's existing quantum hardware sales?
So technically, the networking piece is just an extension of the original thinking that Chris and Jung Sang had, right? And so our scaling strategy has always been kind of single core operation, high performance, single cores, long chains, moving to multi-cores. That multi-cores kind of gets beyond the limit of what you can start to achieve in a single chain. That's you start to get to shuttling and multi-core work. But then you need to move chip to chip, right? And that's where our photonic interconnects come in. That all relies on generating a photon, right? And so the technology associated with frequency conversion of a single photon, being able to do switching of single photons, is all in line with what you need to do to scale to multiple QPUs. And so for us, the logical leg of being able to use the ARLIS contracts, use the Air Force contracts, is an opportunity for us to kind of extend our technical roadmap aligned with the interests of kind of the blind quantum computing and the secure communication aspects, and as well as the heterogeneous kind of work and the kind of conversion to telecom to support the research agendas of the Air Force. And so that's why those two, customers in particular, are extremely, excited to work with us, and we're excited to work with them, because for IonQ, this is an opportunity for me to kind of accelerate our technical roadmap through these collaborations. It's super exciting.
We think networking is a massive market. It's going to be on the same scale as quantum computing. We think same order of magnitude. And if you've been listening to our earnings calls, we've been talking about networking for about the last year or so. And so what these deals represent, the $54.5 million with AFRL, the $5.7 million we announced with ARLIS, these are examples of that networking thesis coming to fruition and working for us. But what's important, as Dean mentioned, is that for IonQ, networking is just an extension of our compute architecture. Technically, there's a lot of synergy between those two areas, and that gives IonQ a great advantage in going after these customers, expanding into that market.
What's exciting about it for us is there's already an internet, right? And the internet relies on fiber optics. For us to scale in quantum, we have to use what already exists in the existing telco infrastructure, and that's how we're architecting. So how we're going to build and be part of that TAM is we're building so that our computers work with existing fiber optics. His team is working as part of the FRL contract on exactly that. How do we make sure that quantum computers can work on the trillions of dollars of fiber that's already existing? That's super exciting for us.
And about the technology side, will photonic interconnect technology be demonstrated by the end of this year, as IonQ mentioned early this year?
So you're going to see downstairs. So the systems, we have systems both in our College Park facility as well as here that are working on photonic interconnects. Those systems have different capabilities. And so the work that we've been doing is continuing to move along that roadmap. Now, we've published a couple milestones that we've already hit. We're making good progress. We already have working systems. And so as we scale the photonic interconnect technology and go from kind of the lab kind of demonstrations and capabilities into improved, photon capture, improved, Bell State Analyzer operation, higher entanglement rates, right? These transition from these demonstrations into more just vanilla engineering, right? We have to go through the optical designs. We have to go through the other risk reduction activities. We're looking at performance and trying to understand where the cliffs and knees are. And so I would say that keep watching for more milestones to just be hit. But it's exciting technology. You're going to see some of it working downstairs today.
Well, we have 4 milestones for photonic interconnects, but which one do you think is the hardest?
The hardest, the way the current milestones are defined, the first 3 are logical kind of progressions in kind of the early demonstrations. Then 4 is the very last, right? Kind of the last, if you will, demonstration. You can imagine that between 3 and 4, internally, there's a huge number of additional checkboxes to check.
Right.
And so, because the fourth one involves full networked, switched, single photon switching over a large multi-core system. The third, however, is basically just connecting two QPUs.
Right.
So I expect that, you can kind of look for, we will be talking more and more about photonic interconnects over time. And we're going to kind of open the aperture of like what is between milestone 3 and milestone 4 from a technical perspective, because when you start to peel back the covers, you can start to see the buildup of the capability, the different kind of interconnect topologies that exist, the entanglement generation rates, and kind of some of the science and the engineering that's kind of going in behind the scenes.
It's fair to say probably, Dean, that the first 3 milestones are demonstrating this incredible capability, which is to tie multiple quantum computers together, multiple QPUs together. And then that fourth milestone is all about scaling that up so that you can go from 2 systems to 3 or 4 to 10, right? And start to build hubs. So that's a difference between demonstrating the technology in production and then scaling it in production.
Then when do you expect error correction and photonic interconnect technologies be implemented on IonQ's commercial systems?
Well, we've already explained that for our AQ64 systems and for Tempo, we will not need photonic interconnects to be performant, to be able to achieve those kind of both the fidelities, the number of qubits, and the overall performance.
Right.
And so we do expect, though, in that Tempo timeframe to be able to start rolling in other kind of capabilities that you need to do more advanced, I would say, quantum error correction demonstrations. So we're going to have mid-circuit measurement, reset, those kind of things that will allow full use of like the partial error correction techniques like the Clifford noise reduction that we just talked about. So that's going to be part of the capabilities that we have in our Tempo timeframe. Now, the systems beyond Tempo are going to be the ones where we continue to invest and continue to realize some of those kind of partial error correction, partial error mitigation techniques. You're going to be able to run those systems in kind of a logical mode in which you can exploit this is at the software layer, being able to exploit logical qubits, right? But those are going to happen in the system or the generations after Tempo. We're going to see that technology get to a point where it's mature enough that it just becomes just part of the architectures.
We saw that Dr. Chris Monroe's lab at Duke has received federal funding from the National Science Foundation's National Quantum Virtual Laboratory to build a 256-qubit system by 2026. Should investors view this work as part of IonQ's roadmap and its implementation of photonic interconnects? Is it related to IonQ?
So the beauty of our relationships with Duke and with the current research that's going on with both Jung Sang as well as Chris is our licensing agreements that we have with the technology that comes out of the labs, right? And so that will continue over time. So as new technologies developed, as they're investigating and doing kind of novel and unique things, we have the licensing rights to that technology. Thomas can kind of speak to the explicit details. I just am the beneficiary of that learning. And so as they work that program and as they learn and as their unique things, IonQ in our licensing agreement allows us to be able to kind of work with Chris and Jung Sang to be able to figure out what IonQ needs to pull in, and we have that option.
But what we don't mean to say is that we don't direct research at Duke. We'd love to, but they are an academic institution that do brilliant research that we benefit from, often because they are able to look very far into the future and say, this is a technology that we need to do some research on. A lot of them fail, and we get the benefit from the ones that work. And as such, I wouldn't look at what Duke does as an extension of IonQ, although we have many fruitful cooperations with them when we work on some projects together, like we did when we did error correction for the first time, or the first company to show that on a working quantum computer.
When you go downstairs, when you're doing the tour, you'll see we have a patent book. And you'll see exactly it needs to be updated, but you'll see that we have US patents, we have global patents, and we share many of those patents with Duke and with the University of Maryland. So it's a visible representation of how proud we are about the collaboration, and you'll see it in the patents that were granted, as well as what we have pending.
And I just visited the Duke Quantum Center 2 weeks ago,
Oh,
right?
yeah.
And so, like, Chris and Jung Sang are doing some amazing work there, and so it's always great to see, like, just the collaboration, to be honest.
And Chris continues to advise us, as does Jung Sang, and has been a part of our calls, because he is, and will always be, a great co-founder with the bleeding edge knowledge.
I was
Right.
just with Chris last week.
Right, that's great. And then one of the biggest concerns we as investors have is that when quantum computers become powerful enough, the government might intervene and prevent IonQ from selling as many quantum computers as it wishes. What are your thoughts on this potential government intervention? And do you have any plans to address such unexpected challenges?
So if you look at the US and how we have developed as a country and how many technologies really have come out of the US, how many technologies have come out of other countries and been adopted here in the US and extended, it's not in the government's interest to restrict the development of new technology. What we have seen for certain types of technology is that there are limits put on which areas you're allowed to sell them, and typically, like very high-end technology and defense technologies, you are not allowed to sell to Russia or China.
Right.
We don't really see them as being the largest markets for quantum computing, not in the near to medium term. In the future, nobody knows. But I don't see that as a problem. If you look at all the other industries in the US that actually have restrictions, these are giant industries. And so we think that any restrictions that the US would put would just be to protect this industry from bad national actors. Now, we can disagree on who's a bad national actor, but I don't think that there's any malintent, and the government cannot develop quantum computers. And so if they restrict that development, they just hurt themselves. So we're not worried about that.
The other thing to think about is, as Thomas said, all quantum also uses classical, right, when we do our work. And I worked on classical.
Right.
And the largest markets in the world for classical, where there are large dollars already invested, as well as the biggest checkbooks, are the US, Japan, UK, Germany, France. South Korea, because of the government's promise to put in money into the country, rocket South Korea up higher than what it had previously invested in high performance or compute. Those are very large markets, the largest ones in the world, and those are not on the list of bad actors. Those are the lists of where we as a global, team are going to go invest. And so I think the marketplace for our quantum computers is massive.
So that was the last question. So lastly, is there anything you would like to say to the viewers?
Thank you.
Thank you.
No, seriously, thank you for all the support that we see and for how detailed you follow our development. Because normally we get questions from people who have not read all the detail and don't understand quantum.
Right.
And so to be able to have an engaging conversation with questions that actually stretches what we can say and what we even know, that's a benefit to us.
And just like you're all learning about quantum computing and about IonQ, so is the rest of the world waking up to the industry. So it's great to be able to host you today and to be able to share so that you can go spread the knowledge about what it is we're doing here and what a quantum computer looks like, which most people in the world haven't seen yet. That's a big pleasure for us to be able to have you all here and to have such an engaged investor community.
Speaking of which, how many people here have ever held a quantum computer in their hand? I think, Dean, you should do the...
We have multiple generations of our trap that we use for our systems. The systems that we have in Forte Enterprise utilize what we call our EGT trap, our evaporated glass on metal trap. So it has a glass substrate, and we deposit metal, and finally we deposit gold on top of that to support and kind of reduce charging and kind of the overall environment. This is our generation of trap beyond that. This is a multi-layered glass trap. And so it's still built right now on a glass substrate, but it uses lithography techniques to be able to do buildup of multiple layers. And so what we can do is generate routing, higher density, we can support vias and other things in the chip itself. And basically that additional routing and additional kind of density allows us to put more qubits, more ions on the system. And so the other thing is just from a manufacturing perspective, we can now leverage a lot of the semiconductor techniques. So we work with some custom fab houses to be able to work this. And so this is the systems these are the chips that will be going into our tempo systems. If you're ever out in College Park, this is the current set of chips that are in all of our barium development platforms. And so it's exciting. We'll pass it around and you can take a look at it.
Today, as you go through and ask questions of us and you go to our factory tour, what Dean's team works on and what we all work on is making sure our performance benchmarks are world-class, and they are. We have to make sure our scale is world-class. The roadmap can scale, the IonQ, all of that. And then another part that we really focus on here that's quite different from other companies is we have the only factory in the United States that builds quantum computers in order to scale them, because we've already shipped a computer to Basel. So think about that as a part of our DNA that's very different, right? We want to get to enterprise grade. We're building computers that you see here that are being shipped into different countries, and we did it first. And we're incredibly excited because that's where you're going to see multiple scalable computers being built here, shipped so they go into other data centers. Most of the other companies in quantum don't do that. Not yet. But what's great about manufacturing? You got to get on that curve early. Whoever starts on any manufacturing, you start early in order to learn, and you develop, and you're on a different learning curve, right?
I have some question on the photonic interconnect, especially when you scale it. As you scale it, your challenges will scale together, right? So coupling two local, what you call it, quantum processor together is different than connecting 10 or even beyond, right? I can just, with my very limited knowledge, I can think of when you couple your local qubit to the photon, you have some, how do you control in synchronized manner? Also, as you remote, qubit will probably decohere faster than the local, and then you have so many things. How do you synchronize and control sort of those when you scale? Can you name a few challenges in that scaling? And then also comment a few approaches and strategies you're taking in that.
So right now, the synchronization is definitely an issue, right? And so you have to be able to have very clear time synchronization between the systems. So when you go on the tour, you'll see the hardware that we use for time synchronization downstairs. And so that's part of it. Now, the overall topology of the chips in terms of the physical layout of the individual trap, as well as where you do light collection, that represents R&D that we're actively doing right now to ask ourselves, how many interconnect zones are there on a single chip? Is there different topologies that you can create, mesh networks, star networks, whatever type of other networks to be able to connect systems? Because at the end of the day, if I do my job right, I'm shrinking the system size down, and I'm also creating higher performance, more robustness, better scalability, and we're being able to network these together so that a single machine will actually have multiple QPUs in it. And so the interconnects will be used both for intra-machine as well as inter-machine communication. And so as the distance for inter-machine communication grows, the barium wavelengths will no longer work. That's where you need to start to get to some kind of frequency conversion to get to telecom or longer wavelengths. And so within the confines of a single machine, you don't need to worry about that. You can still use kind of the standard techniques that we have now. And so the part of what we have to do is figure out the time tracking of those photons So being able to think about how you get two photons to the same spot in the same time, know which system generated them, which ion generated them, track all of that. That's the hardware and software we're building now to be able to kind of invest in all of that. It's all the kind of building block technologies that we generally don't kind of do deep dives on in our investor calls or on our blogs, but that is the development work that we're actively doing as we speak and that we already have behind us in part as we move forward.
Are you leveraging some kind of AI technology in such a challenging process?
This is classical, like, high-performance control. So, yeah.
We've got time for about 2 more questions.
I'm AI and cloud engineer. I'm very interested in AI agent system nowadays. So I'm studying about the AI agent application who study some on the difficult topics such as quantum. So it is inspired by Sakana AI, the Japanese one. So my question is, do you use the kinds of AI technology to study and to develop your products?
So we have a roadmap that includes the use of more advanced, I would say, decision-making techniques. So most complex systems have a hierarchy of decision kind of logic, whether you're doing things that are inside of a single chip, right? Analog control. Go up to where you're looking at FPGA, things that are operating on FPGAs and system on chips. Things that go above that in terms of the logic. And then you get to some of these more supervisory type of pieces that are looking at that. So right now, I don't want to speak to specifically the kinds of techniques that we're using, but the intention is to have a software stack as well as a richness of, I would say, ability to use the best technique to get the right answer. So I'll leave it at that. AI is part of that mix. Machine learning is part of that mix. Classical techniques are all part of that mix.
Can I just add to, as we said, we have hardware, we have software, we have the algorithms, we have services. A really big area that IonQ is investing in is in the algorithm part. How do we look at how quantum can be helped by AI? So we have a very large applications algorithm team. Actually, Dr. Masako Yamada will actually be speaking at the Quantum Plus AI conference, which is going on later this month. And she is one of our premier employees that has been working on high-performance computing as well as now quantum. And she's going to talk about how does IonQ look at AI's impact on impact as well as interconnection with quantum. And we'll also be having a webinar that will talk about some of the different algorithms that we're working on and how does quantum help this supercomputer, using AI. We have incredible work going on. We're excited to talk about, in particular, a lot of the applications that we're working on.
So you can think of it that there's a certain aspect of quantum helping AI. I'm also interested in designing, as I design our systems, how AI can help quantum, right? Like,
I just have a simple question. Do you have any relationship or collaboration with Zapata, which is, co-founded by my professor, Alan Astrofuji? I just want to know how do you have some kind of relationship or some collaboration task between Zapata, which is quantum software company?
So we maintain relationships with many of the quantum computing startups and other companies in the space. That's something that we always like to make sure that we're in collaboration and in connection with them, because we really view it as a full industry that's growing at the same time. Zapata we published work with many years ago, but we don't currently have an ongoing relationship with them. Yes, that's all the time we have. So thank you everyone for joining us for the Q&A, and we will wrap up and then proceed to the lab tour.
All right, thank you.
Okay,
Thank you all.
very much.